Hi everyone, thank you for being here today. My name is Mạnh Lương Nguyễn, and now I'm gonna introduce our new work, FedMAC, tackling partial modality missing in federated learning with cross-modal aggregation and contrastive regularization. So first, let me introduce some terminologies. Decentralized multimodal learning refers to gathering features from multimodality data to increase knowledge for the model. For example, in here we can leverage the information from text modality, images modality, and signal modality in order to increase the knowledge of our model. And in this centralized context, missing modalities refers to an incomplete data set, which means that there are some of training or inference samples may miss some modalities. In addition, federated multimodal learning refers to collaboratively training with clients who have different modality sets, and the missing modalities here refers to dealing with the diverse set of modality, and each set corresponds to a client. So this brings some of confusion here. The missing modalities in those contexts are totally different. So in this work, we define two new definitions of missing modalities in federated learning apart from the full modality one. First is complete missing, and it refers to separate modality subset per client, and it is commonly researched in the federated learning community. However, in practice, each client may have incomplete local dataset, and it refers to partial missing. For example, top-tier hospital register that they have 5 modern sensors, which corresponds to 5 different modalities. However, one or some of them may be in maintenance in some period of time. So it will create a local incomplete dataset referring to partial missing. And also, the empirical results show that the effect of partial modality missing will be much more negative compared to the complete modality missing. So those scenarios lead to our motivation of how to design robust algorithm and how large the impact of partial missing can be. So let me introduce our new framework to solve this problem. So FedMAC is built up on a hypothesis that a modality is actually an augmented version of a core hidden feature. For example, an image of a cat and its sound should be considered as an augmented version of some cat feature which is hidden. And this cat feature will be the most essential part in order to decide whether the input is a cat in the real scenario. So we have an assumption here. If the core feature is extracted completely, our model won't be affected by the modality subset of each instance. Additionally, in federated learning, there are two different phases. The first is client training, and the second is stable aggregation. And in this work, we focus on the local client training design, and we utilize a common approach of stable aggregation, which is Fed average. So in terms of client architecture, first we adopt a missing aware encoder in order to extract the shared core feature from different modalities. However, remember that in partial missing, some modality of the raw input will be missed, and the feature that are extracted from those modalities should be nonsense. They contain no information. So those information will be replaced by a corresponding evidence in order to learn a hidden knowledge of that modality. However, this approach contains some limitations. One of them is the imputation embeddings are shared among the instances. So this embedding cannot represent the core features of each instance completely. So this raises a necessity of reformulating missing modality features from existing ones, allowing for instance level specification. How can we do that? So in this work, we introduce two new modules. The first is cross-modal aggregator. So this cross-modal aggregator will map space share feature into a higher level space to learn the modality-wide similarities. And this modality-wide similarity will be used to guide back a weighted aggregation in the shared space. However, remember that the benefits of the aggregated feature for existing modality features might be less than the missing one. It is because that the feature which are extracted from the existing modality feature should contain much more information of the raw input compared to the missing ones, which are imputed by the corresponding embedding. So in order to balance the contribution of those features, we design a global fusion module which will dynamically fuse the feature before and after the aggregation in order to generate a final representation. And this final representation will be fed into a decoder for prediction. However, there are two problems in here. The first, we cannot ensure that the representation generated from the missing aware encoder will be a coherent feature. It will be in the same space without any regularization. And the second problem is that we cannot ensure that this aggregation will be useful or it will become trivial and useless to like for the feature reformulation. So to address to those problems, we first introduce a spatial loss. So this spatial loss will ensure that all modality-specific features belonging to a single instance are closely aligned in the shared space. And we define that the modalities of the same instance will be the positive pairs and negative pairs for otherwise. So look at the equation here. The R actually a similarity matrix, and we are trying to push all of the modality representation in the shared space to to be closely aligned, and it will ensure that the representation of extracted from different modalities should represent the same information. The second loss we propose is modality-wise similarity loss, and it will preserve accurate cross-modality relationship within the shared representation space. And similar to the spatial loss, we define the positive pairs for the modalities that come from the same instance and negative pairs for otherwise. And the equation also show that we are trying to push the representation in the modality-wise similarity space to be closely aligned if they are belonging to a same instance. And this ensures that the model can learn the cross-modal relationship accurately among different instances within a batch. Altogether, we have a final training loss, which consists of three components. L task, which can be cross entropy in the classification task. L share, which is spatial loss, and L sim is actually a modality-wise similarity loss. And the lambda here control the effect of the contractive loss into the final training loss function. In terms of experiment settings, we use a subset of PTBL dataset, and each sample in this dataset has 12 modalities and is assigned to a single class. One interesting thing in our work is how we simulate the partial missing modality data. We define a new term, missing pattern or missing statistic, PM and PS, and we assign them to a client K with a dataset DK to formulate a missing metric of VDK as you can see on the slide. So with this VDK will contain different BIM, and BIM is a binary value and it indicates whether the modality M is missing or available for sample I. And MK and K here are the number of modalities and the samples of that client. Finally, the partial missing modality instances can be obtained by the matrix multiplication between the missing matrix and the original local dataset. So here is a visualization for how the missing pattern can change the local dataset. And the figure is visualized in case that PM equal to 1 and PS equal to 0.5. And you can see on the figure here, you can recognize that 100% of the samples of the local data set will be missed 50% of their samples. In relation to quantitative results, first we test our approach under a scenario that the missing statistic of clients and server are similar. And we observe that FedMAC consistently outperforms other baselines in all tested missing scenarios, especially when the missing statistic increase. For example, in the case that PM equal to 1 and PS equal to 0.8 in both ID and non-ID setting. Other observation in both while other method performance significantly great. FedMAC consistently remains robust when missing statistic increases in the ID setting. Furthermore, we test our approach under the much more complicated scenarios where the missing statistic of clients and server are different. And the observation here were that first baselines perform relatively well with lower missing statistic, which struggle as the server missing statistic increases. In contrast, FedMAC maintains strong performance, consistently achieving the best result across nearly all experiments. In terms of evaluation studies, we evaluate two key components of FedMAC in the ID setting, where the missing statistic of clients and server are similar. We introduce two variants, FedC, which is FedMAC without cross-modal aggregator, and FedMA, which is FedMAC without contrastive regularization. So the results show that FedC perform adequately when the missing modality pattern is uniform. For example, PM equal to 1, which struggles when PM smaller than 1. FedMA show notable performance declines, particularly in scenario PM smaller than 1. So this observation underscores the role of contrastive mechanism in our framework. Finally, FedMAC outperforms FedC and FedMA in most cases. So overall, both the cross-modal aggregation and contrastive regularization in FedMAC is crucial for robust and consistent performance in the partial missing context. In conclusion, our contribution involves first, we are the first to thoroughly investigate the problem of partially missing modalities in FL. And we also introduce FedMAC, an innovative plan-side architecture designed to handle the partial missing modality in FL. For the result, it showed that our FedMAC consistently outperforms baseline with a large margin in every testing scenarios when the missing statistic of several clients are similar. And it also outperforms existing methods in most cases when the missing statistic of several clients are different. For future work, we are gonna conduct more extensive experiments, including different datasets and varying missing scenarios. And also, we will try to design an appropriate server aggregation algorithm instead of Fed average, which can handle partial missing modality under non-ID setting. So that's the end of our presentation. If you have any question, you can ask us, and we will try to give you the best answer. Thanks for listening.